Okay, this is still lesson 7, and I'm assuming that by this time everyone has done the first part and has experimented and used the circuit board and figured out all of, or at least saw all of what you were supposed to see there. So what I'm going to do now is to explain in detail what happens. And sometimes you need to know what happens in like the details of exactly what's happening, and then other times you can use more general descriptions. But what we're going to do now is we're going to say that we're starting out with the capacitor uncharged, and then we're going to move the switch from position B over to position A. And something else you might do is you can modify your answers to step 11 or add to them if you need to. So we're going to move the switch over to this position. Okay? Now, something that you might think about, what is a battery? Well, it applies a voltage, but what does that really mean? So, an idea about a battery in terms of things that you are probably perhaps already familiar with is if you think of a battery as an electron pump. Now, depending on what the actual battery is, the power supply or whether it's a dry cell battery, various things actually happen there. But it's going to work best if we think of this as an actual battery. And inside a battery there are chemical reactions, which we're not going to do. But it emits electrons from the negative side. So when there's a complete connection, then this can emit electrons from this side. So then the electrons travel through the wire. Now notice I am talking about electrons, not protons, because electrons are actually the charges that move. When we're talking about current, the standard notation or the standard idea is to talk about the direction positive charges would move if they did, but they don't. So for right now, we're not going to talk about current. I'm going to talk about electrons. So electrons come out the negative side of the battery, come over here, and somehow they can realize that this is not a complete circuit, so they don't go this direction. They go up this direction. Now, the symbol for a capacitor is drawn that way for a reason. A capacitor is at least one version, is two parallel plates that are conductors. So, and they are separated by space, either air or some insulator, so that the electrons cannot jump across the gap. So the electrons go up here, and then there's a metal plate there that they can travel on or move around on. So what happens then, the electrons are not created in the battery, but electrons from the other side of the battery have to be pulled in so that they could be emitted over here. So if they're pulled in from here, they have to be pulled from some region, so they actually end up being pulled from the other parallel plate. So what happens then is electrons build up here, and I'm just going to draw 4 of them. And for 4 electrons to be here, there had to be 4 electrons that left the other plate, and so that's going to leave the other plate as positive. Now, so we say, well, okay, electrons are going. Now, if you remember at the beginning when you first closed the switch, the light was on and it was fairly bright. So the electrons were moving kind of fast. But after you get a bunch of electrons on a finite plate, they all kind of begin to look around and see each other and, well, I don't really like this other electron. So after a while, there's no more electrons can be put on there because they're trying to repel each other and there's not enough room to put them on there. So by that time, the current has died down. It's like students coming into a room. So you have students, or maybe they've all been standing out in the hall and now you've opened the door and let the students come in. They all rush in to begin with, and then there are a few stragglers. So you get electrons building up on this plate, and as a result then the other plate is positive. So this will happen until there is a certain amount of charge on the capacitor. Now at this point you don't really have to know what the equation is, but I'm going to go ahead and write it because just in a little bit farther in the lesson it will talk about this. But the equation is that charge is equal to CV. Q is charge, so the charge on the maximum charge on the capacitor is the capacitance of the capacitor times the voltage. Now the capacitance is a number that's characteristic of the actual construction and the geometry of the capacitor. And I think if you remember in one of the previous lessons when it talked about resistance, the resistance of a resistor is based on the material and the size and shape and the geometry of the actual material. So the capacitor is based on how it's constructed. Okay, so you can tell here from the math point of view, if you have a particular capacitor, if you were to have a larger voltage, you could end up with a larger charge. So if you have a stronger battery, it's capable of forcing more charge onto the capacitor. But for right now, the idea is with the switch to position A, the light bulb came on fairly bright and then it slowly died out. You probably don't want to say that the bulb came on and then turned off, because that might imply that it was on and then it went out all at once, and that's not what happened. So it was on and then it slowly went out. Okay, so we have the capacitor charged, and now we're going to move the switch to the other position. So I'm going to move this from here back over to here. And at this point, the charges realize that there's no battery or no power supply here making them stay. So they're very happy to leave and go back around to the other side of the capacitor. This is analogous to at the end of the period when the bell rings and the students jump and run. So when you first close this switch, it's like all the kids are leaving the classroom. So the charges immediately start going, and that's why the light is bright. Then after all of the charges get back to the other side, there are no more charges to flow, so there's no current, so the bulb has gone out. Again, it's probably best to not really say it goes out. You could say it, or you need to say it slowly goes out, to imply that it's a fading of the brightness and not that it's totally on and then is totally off. Okay, so that's an explanation of what happens when you're charging a capacitor. Now, the other part of the experiment had a 48 bulb, and I don't think there is another experiment that we have done at some point that looks at the resistance of the light bulbs. Actually, you could just measure the resistance. That might be something to do. Measure the resistance of the number 41 and the number 48. And at this point, you have already measured the... Oh, actually, I may have had you to do that. you had done the resistance for the 48, the R of the 48, in a previous lesson, and that was about 4 ohms, 4 to 5 ohms. And if you measure the resistance of a 41, you will get about 1 ohm. So the 48 has higher resistance. Now, when you left the 41 over here and the capacitor charged, then when you put the 48 on the B side and move the switch to there, you should have seen that the initial brightness, which was one of those questions, the initial brightness of the 48 was a little less than the initial brightness of the 41. Sometimes that's hard to tell because you're not seeing them at exactly the same time. But the 48 should have been a little less bright, but the thing that you should definitely been able to tell is it took a lot longer for the 48 bulb to go out than for the 41. So then the question is why? Because you haven't changed the capacitor and you haven't changed the voltage. So why does this light bulb behave differently? Well, if it has more resistance, you know that more resistance means that it's not going to let the current or let the electrons flow as easily. So they're not flowing as easily, which means, to begin with, which means that the bulb is not as bright because brightness goes with the current. But then you have the same charge here that needs to get back around. Now, if the charges are moving slower, then for them all to get back around to the other plate, it's obviously going to take a longer time. So that's why with the 48 bulb that it was initially not quite as bright and why it took a lot longer for the charge to get back around and for the capacitor to discharge. So the rest of this, there are several parts to it. One part is to derive some equations for adding capacitors in series and parallel, and it leads you through that, and particularly after you've been through the one deriving the equations for resistors, you have an idea of how that's going to work. There are some explanations about actual graphs of current and voltage that we did at one point in the past using some other technology. I have those there mostly just for information. And then there's the last section that's on an inductor. An inductor is basically a coil, and it behaves somewhat like a capacitor, actually kind of the opposite, but it's much more difficult to observe light bulbs than with the capacitor. So we didn't really have you to do an experiment. But there's some explanations there and about what's happening and some graphs about the current and voltage, and also what was the last part? About adding inductors in series and parallel, and there's no derivation for that because it's a little bit more complicated, but I did give you the equations and then I have you to write them in a box so that kind of is a little bit easier for you to remember. So the information about the capacitors and inductors, a fair amount of that we will make use of toward the end of the next unit, which is on alternating currents.